A very good afternoon to all my dear students. In this video lecture, I will be covering the concept of block diagram representation and reduction of block diagram into simple or canonical form to obtain the transfer function of a control system. So as you can see in the figure, this figure represents a liquid level control system. Okay. So here the control system works like this. There is a pneumatic valve which operates to the flow of the liquid, and the liquid flows from this pipe to the tank. Okay. And the height of the liquid is maintained. And this float measures the height of the liquid, whether it is up or down, and gives feedback to this controller, and the controller in turn operates the pneumatic valve either to open it or close it, and the liquid from the tank goes out in the form of the output. So this is a simple closed loop control system. So this control system can also be represented in the form of a block diagram for analysis purpose. Okay. So we will start with the input. The input to this system is the desired level of liquid in the tank. Then this is the summing point. Then the signal goes to the controller to increase or decrease the valve opening, operating the pneumatic valve, and that will give liquid to the tank, and the actual level of liquid is the output. From here, the signal is taken off for feedback, that is through the float position, and the float position is also given as input to this summing point. The summing point compares the desired liquid level and the actual liquid level, and the error signal, that is the difference in liquid levels, is fed to the controller, which in turn acts by operating the pneumatic valve to maintain the liquid level in the tank. So this type of representation is called as the block diagram representation, which we have already studied. So using this block diagram representation, we can obtain the transfer function of a control system. Okay. So now coming to the simple or canonical form of a closed loop control system. Simple or canonical form of a closed loop control system. To obtain the transfer function of a control system represented in the form of a block diagram, we have to reduce that block diagram into this simple or canonical form. As I have already explained in the online class, the simple form or the canonical form of block diagram has one block in the forward path, one block in the feedback path, one summing point, one takeoff point, one input and one output. This type of control system, this type of block diagram is called as simple or canonical form of representation. And the notations used in this simple canonical form are: R of S is the Laplace transform of input R of t, C of S is the Laplace transform of output, E of S is the Laplace transform of the error signal, B of S is the Laplace transform of the feedback signal, C of S is the equivalent for, G of S is the equivalent forward path transfer function. G of S is called as forward path transfer function equivalent. Then H of S is the equivalent feedback path transfer functions. These are the notations used. Okay, notations used for the simple or canonical form. So in the online class also I have done this derivation, but then also let us see. See, in this case, E of S, that is the error signal, is the R of S plus or minus B of S. That is, here a comparison is made. Error signal is nothing but the output of that comparison. So R of S plus or minus B of S, or minus or plus. Here it is denoted as minus or plus B of S. Let us call that equation 1. Then B of S, that is this feedback signal, is nothing but the output C of S into H of S. C of S into H of S. What is C of S? What is C of S? C of S is G of S into E of S. So call that as equation 3. Then B of S is H of S into CS. Substituting this in equation 1, I can get E of S is R of S minus or plus CS HS. Minus or plus CS HS. So E of S is equal to C of S. C of S, E of S is equal to C of S by G of S. Okay. So substituting all of that is from equation 2. So this we get from equation 2. From equation 2. From equation 3. It is from equation 3. E of S is C of S by G of S. So C of S by G of S is equal to, I am substituting this here, R of S minus plus CS HS, or C of S is equal to RS into GS minus plus CS GS HS. Okay. So with this we get C of S into bracket, taking C of S common, into bracket 1 plus or minus GSHS RS into GS, or C of S by R of S is equal to GS upon 1 plus or minus GS HS. Okay. This is one formula which we are going to use. Remember, the transfer function C of S by R of S is G of S, that is equivalent forward path transfer function, divided by 1 plus or minus. That is, if the feedback signal is minus, then we have plus here. If the feedback signal is plus, we have minus here. Then GS into HS, where HS is the equivalent feedback path transfer function. Okay. So this formula is called as the transfer function of a simple or canonical form of representation. Use plus sign for negative feedback and negative sign for positive feedback. Okay. So this is clear now. So that we can represent also as in the form of only one block. That is, this form can be represented like this. R of S is the input and the block transfer function is G of S divided by 1 plus or minus GSHS, and output is CS. This can be used as a standard result to eliminate simple loops in a complicated system reduction procedure. Okay. So I had showed you here that the block diagram can be like this. The liquid level system can be like this. So any number of blocks in the forward path and any number of blocks in the feedback path, they will be reduced with the help of block diagram reduction rules to obtain the simple or canonical form of transfer function, simple or canonical form, and applying the canonical formula, that is G of S divided by 1 plus or minus GSHS, we can obtain the transfer function of a complicated block diagram. Okay. So now the block diagram which has many blocks has to be reduced to the canonical form. So for that we use some rules which are called as block diagram reduction rules. Any complicated system, if brought into simple form or canonical form, its transfer function can be calculated by using the result derived earlier. To bring it into simple form, it is necessary to reduce the block diagram using proper logic such that the output of that system and the value of any feedback signal should not get disturbed. This can be achieved by using following mathematical rules while block diagram reduction. So now I will be dealing with the block diagram reduction rules one by one. Okay. These rules I have also explained in your online class. Please go through the video lecture. Whatever you have not understood in the online class, you can go through this video lecture. So rule 1. Okay. Rule 1, the associative law. Okay. What this associative law says is, consider two summing points as shown in the figure. Let me say this is summing point 1. This is summing point 2. Okay. So if these are the two summing points, to summing point 1, the input is R1 and one more input is going from this side, that is R2 with a plus minus sign. R2 is with a minus sign. So the signal here is R1 minus R2. So that will be output to, that will be input to this summing point 2. And one more signal, that is plus R3, is going to this summing point 2. So the total output is R1 minus R2 plus R3. In between these two summing points, there are no blocks, no takeoff points, nothing. In this case, as per the associative law, these two summing point positions can be interchanged. These two summing point positions, they can be shifted. The right one can be brought to left, left one can be brought to right. If we do that, see what happens. If we do that, this is the situation. That is, this is summing point 2 now, and this is summing point 1. Okay. So now, along with summing point, the signal also we have shifted. So now R1 is the input to summing point 2, and it already has plus R3 as one more input. So what is the output here? R1 plus R3. To summing point 1, R2 is also there. So R1 plus R3 minus R2, this is the output. So you can see that this output and this output are the same. So as per associative law, if you interchange the position of summing points in the block diagram, so while solving the block diagram problems, if you interchange the position of summing points such that the summing points don't have any block or takeoff point in between, then that is not going to affect the output or the feedback of the control system. The logic is not, this one in the orientation of the block diagram is not disturbed. Okay, that is rule number 1. Moving to rule number 2. Okay, so this is rule number 2. Rule number 2, blocks in series. Okay, so in a block diagram, we may have blocks continuously connected like this: G1, G2, G3. What is input to G1? R of S is the input to G1. So that gets multiplied and the output will be R of S into G1. Then comes G2. Then what will be the output here? R of S into G1 into G2. Then that will be input to G3. So R of S into G1 into G3 into, G1 into G2 into G3 is the output. R of S, G1, G2, G3. Okay, so that is the output. So if this is the output, then these blocks which are connected in series can be represented by only one single block whose transfer function is G1 into G2 into G3. Instead of 3 blocks separated as G1, G2, G3, they can be treated as series blocks and their resultant or equivalent transfer function will be the multiplication of the 3 transfer, so 3 this one, that is G1 into G2 into G3. So this type of representation is called as blocks connected in series. But the only thing we have to remember is in between these blocks, there should not be any takeoff point or summing point between the 3 blocks. Okay, that is the key point. If there is a takeoff point or a summing point in between the blocks cannot be said to be in series. Okay, that is rule number 2. Now coming to rule number 3. Okay, coming to rule number 3. Rule number 3, blocks connected in parallel. So look in figure 5.14. G1, G2, G3 are the blocks connected in series. That is, the same input R of S is going to G1, G2 and G3. After this, the output here is R of S into G1. The output here is R of S into G2. And here it is R of S into G3. So all those outputs again come and get connected at this summing point. This R of S into G1 connects with a minus sign, this with a plus sign, and this also with plus sign. That is, they get summed up. All the 3 inputs get summed up. So output will be R of S into G1 plus R of S into G2 plus R of S into G3. So now if you take R of S as common, I have to take care of the signs. This is minus R of S. If I take care of the signs, so C of S is equal to R of S G1, R of S G2, R of S G3. Taking R of S out, so this is G2 plus G3 minus G1. So this can be represented as only one block, that is minus G1 plus G2 plus G3. That's why if blocks are connected in parallel as shown in the figure without any takeoff point or summing point in between them, and the signal starts at one point and the signal from these blocks goes to a common summing point, they are treated as parallel blocks. They are treated as parallel blocks and their output is the algebraic sum of individual transfer functions. Okay. So blocks which are in parallel get added algebraically. You should remember, blocks connected in series get multiplied, while as blocks connected in parallel get added algebraically. This is rule number 3. So now coming to rule number 4, shifting of a summing point behind a block. Shifting of summing point behind a block. So consider the situation shown in 5.19. That is, there is a block with transfer function G to which an input R is given. The output is RG. The output is RG. And one more signal plus Y goes at this summing point. So the output here is RG plus Y. You can see. Now what I want to do is this summing point SP, I want to bring behind this block, shifting a summing point behind the block. So after shifting the summing point behind the block, I should not have any change in the output as well as the feedback or the signal going to the summing point. I want to do it like this. Okay. I want to take the summing point from this point to this point, which I have taken now. So to this summing point, the input is R and this signal, let it be X. Let us say it will not be Y because we have shifted it. It will not be Y. So let us say it is X. Okay, let us say it is X and G is as it is. Now we will see what is the output of this block diagram earlier. RG plus Y. The output was RG plus Y. But what is the output here? Output in the figure 5.20. See here. Here it is R plus X. R plus X into G. So G into R plus X or RG plus XG. Okay. RG plus XG. Here from first figure it is RG plus Y and from the second figure it is RG plus XG. But for us both have to be the same. Okay, both have to be the same. So if I equate both of them, I get XG equal to Y or X is equal to Y by G. Okay, my signal is Y and I want Y by G. If I want Y by G, what I can do is I can multiply the signal y. I can multiply the signal y with a block which is having a transfer function of 1 by g. So now you can see if I multiply the y signal with multiply means I will connect in series. Multiply means I will connect in series with a block 1 by g. That is, I have shifted the summing point behind this g. So 1 by g I will take here. So now what happens? R plus y by g is the signal here. R plus y by, so C of S will be what? R plus y by g into g. That is equal to Rg plus y. Rg plus y. Is it correct? So this is what we want, isn't it? So whenever you want to shift a summing point behind the block, you have to add in series the reverse of the block, that is 1 by g on the path of y. Okay, that is what we have to do. So this is rule number 4. So now moving to rule number 5. Okay, rule number 5 is nothing but in rule number 4 we shifted the summing point behind the block. Here we are shifting beyond. Behind andre ಹಿಂದೆ ಮಾಡಿದ್ವಿ. So beyond means after. This is behind means before. Beyond means after. Okay. We want to shift it. Beyond means after the block. So the situation is as shown in figure 5.2. That is, the summing point is behind the block. I want to bring it beyond the block. So this rule I will not explain in detail. I will just give you the result. Okay, because it is similar to earlier rule. Only thing is we are shifting beyond the block. Here in this case, you can see figure 5.24. If you see the figure 5.24, here what we are doing is, in this case, we are multiplying the y signal or adding in series the same block, whatever was there. Earlier rule, we inversed it and added. Now we are adding the same block so that the output remains the same. So I have not gone into detail of rule number 5 because it is exactly similar to rule number 4. Only thing is, there we shifted the summing point behind the block. Here we are shifting the summing point beyond the block. So when you are shifting the summing point beyond the block, you have to add in series the same block. If you are shifting beyond g, you have to add in series along with y the same block g. Okay, so that the output remains the same. That is, signal y must get multiplied with transfer function of the block beyond which the summing point is to be shifted. This is rule number 5. Now moving to rule number 6. This is rule number 6. Summing point has 2 rules. Now takeoff point. Okay, shifting a takeoff point behind the block. Shifting the takeoff point behind the block. Just shifting only. Rule number 4, 5, 6 and 7 similar. Okay, so consider the block diagram shown in figure 5.25. There is this input R, a block G, and then this output C. There is a takeoff point here. Okay, so takeoff point means it takes the signal. So what is the signal here? Rg. That Rg is taken here also, and that is the output also. So this takeoff point I want to bring behind this G. I want to bring it behind this G. If I have to bring it behind this G, then what I have to do is, in the path of Y, I have to introduce the same block in series with Y. Okay, in series with Y. So that is the rule number 6. To shift the takeoff point behind the block, add the block in series with the takeoff point in the same way, that is, multiply it so that the output doesn't get affected. That is rule number 6. Now moving to rule number 7, shifting takeoff point beyond the block. Exactly similar. This is the situation. So here I want to shift it to the right. If I have to shift it to the right, on the path of the takeoff point, add the signal that is the reverse of the block in series with the takeoff point so that the output doesn't get affected. So once again, I would like to tell rule number 4, 5, 6 and 7 are related to shifting of summing point and takeoff point. Rule number 4, summing point behind. Rule number 5, summing point beyond. Rule number 6 is takeoff point behind, and rule number 7 is takeoff point beyond. Okay, so you have to remember these. Only thing you can remember is for summing point behind the block 1 by G, beyond the block G. Takeoff point behind the block G, beyond the block 1 by G. Okay, you will understand them very easily once you start solving the problem. Let me move to rule number 8. Okay, so go to rule number 8. Rule number 8 is removing of minor feedback loop. Removing of minor feedback loop. Okay, so in the total block diagram, a complicated block diagram, in between, okay, small feedback loops which are in canonical form. Okay, small feedback loops which are in canonical form are observed. Okay, that is, canonical form means it has to be in this form only. One summing point, one forward block, one takeoff point, one feedback block, one input, one output. If such loops, okay, such loops are observed in the block diagram, then reduce them using the formula GS upon 1 plus or minus GSHS directly, so that instead of one summing point, one takeoff point and two blocks, you will have only one block. So this is removing of internal feedback loops or minor feedback loops. That is rule number 8. So now coming to the next rule, that is rule number 9. Rule number 9 deals with multi-input systems where the principle of superposition applies. The principle of superposition I have explained in the introductory class also. That is, if a control system has, as shown in figure 5.31, if a control system has many inputs R1, R2, R3 dash dash Rn, then how to obtain the output? In that case, you have to consider each input at a time. Consider R1, neglect all other, obtain the output. From R1, say you get the output C1, neglecting all other inputs. Then consider R2, get C2. Consider R3, get C3. In that way, the total output C will be summation of these individual inputs. Okay, summation of all these, summation of all the outputs C1, C2, C3 dash dash. See here, you can see this C1, C2, C3 dash dash Cn. So this is called as principle of superposition. So in block diagram reduction, if you get multiple inputs, then you can simplify it using this principle of superposition. These 9 rules are called as the normal rules of block diagram reduction, which are very much commonly used. Then I will be going to rule number 10, which is called as the critical rule. Rule number 10 is the critical rule. Rule number 10 is critical rule. So this is shifting of takeoff point after a summing point. In this case, summing point and takeoff point are side by side. So you want to shift the takeoff point this side. So consider the figure 5.32. In figure 5.32, there is an input R1. This is taken off, takeoff. So what is the signal here? X is equal to R1. The same signal goes here also. The same signal goes here also. And this is one summing point. To this, there is one more signal plus or minus Y. So what will be the output here? R1 plus or minus Y. R1 plus or minus Y. Now I want to get this takeoff point beyond this summing point without affecting anything. So I will show it in figure 5.33 like this. There is this summing point. To this there is the signal plus or minus y, and I have shifted the takeoff point. And the signal from takeoff point, let it be z now. Let it be z. It was x there equal to r1. Let it be z. So z is how much? R1 plus or minus y. Z is R1 plus or minus y, while as x was R1. I don't want to change that. So what I have to do is, if I have to get this as R1, if I have to get z equal to R1, I have to cancel plus or minus y. If I have to cancel plus or minus y, I can add minus or plus y here. So what does that mean? That means that, see here, there is this input R1, then there is this signal plus or minus y, this is R1 plus or minus y, this is R1 plus or minus y, So R1 plus or minus y, I will create one additional summing point here, and to that I will give one more signal which is instead of plus or minus y, I will give minus or plus y. So R1 plus or minus y, minus or plus y, so x will be R1. So when you have to shift a takeoff point beyond a summing point, you have to introduce additional summing point, and to that you have to add the signal in the reverse sign, okay, algebraically reversed sign, so that the system doesn't get affected, okay, so the system doesn't get affected. This is called as critical rule and rule number 10. So now moving to rule number 11. You might have guessed. Rule number 11 is shifting the takeoff point before the summing point. So in rule number 10, I had shifted it after a summing point. Now I have to shift before a summing point. This rule I will not explain in much detail because it is similar to the previous rule. But you remember, if we have to do this, then what I have to do is, I have to introduce a summing point of same, that is, I have to introduce a summing point with the same signal. That is, I will draw it here. There is this summing point. This is C, and this is the takeoff point. This is the takeoff, signal, I got this one. This is the takeoff point. Here is the takeoff point, and here what I have to do is, this is plus or minus y. I have to add one more summing point with the same signal, plus or minus y. Here it is R1. Here this is R1. This is R1. So this is R1 plus or minus y. This is R1 plus or minus. Output is R1 plus or minus y. Here also output is R1 plus or minus y. Okay. So that is how feedback signal X, which is R1, hence Z signal Y, must be added with the same sign. Okay. Here a summing point should be created and plus or minus Y should be added to it so that the output remains the same. That is R1 plus or minus Y. So rule number 11 is called as the critical rule. Rule number 11 is called the critical rule. So I have explained all the rules. Now I will go to that is procedure to solve block diagram reduction problems. Block diagram reduction problems, procedure to solve. That is when you have 11 rules. So how to apply those rules? Those are the guidelines given in this procedure. Okay. Step 1 says reduce the blocks connected in series. The first step is whenever you look at a block diagram which has to be reduced, see if there are any series blocks first. Reduce them. Second step, reduce the blocks connected in parallel. Then the parallel. Reduce the minor internal feedback loops. Then step 4, as far as possible, try to shift takeoff point towards the right and summing point to the left. Then shifting in step 4, shifting of summing point and takeoff point. Step 5, repeat steps 1 to 4 till the canonical form is obtained. Then step 6, using standard transfer function formula, obtain C of S by R of S using the formula. Then one more thing is, unless and until it is requirement of the problem, do not use rule number 10 and 11. So rule number 10 and 11 are critical rules. We have to use them only if necessary. If the problem demands, of course we have to use. Otherwise, avoid using those rules if not required. So in this lecture, I have completely explained the representation of a control system in the form of a block diagram, and then what is simple or canonical form of block diagram, and the formula for simple or canonical form of block diagram transfer function. Then I have explained the 11 rules of block diagram reduction, individually taking one by one. Then in the last slide, I have explained the steps to solve the block diagram reduction problem. So in the next video, I will be solving some problems on block diagram reduction. So all of you go through this video. If you have not understood in the online class, which many of you have not attended, go through this video so that you'll understand the rules today. And tomorrow I'll be posting the video on problems on block diagram reduction. Thank you so much.